here. So Tyler grew up in Marmarth, North Dakota. Does that sound about right?
Yep, that's right.
Awesome. And spent most of his childhood in the Badlands searching for fossils. While completing his undergraduate research at Swarthmore College, Tyler created the Marmarth Research Foundation as a way to get the public actively involved in field paleontology. Tyler's passion for paleontology took him to Yale University, where he completed his PhD before moving on to the Smithsonian Institution for a postdoctoral fellowship. Outside of science, Tyler enjoys competing in extreme obstacle course and relay races and teaching his 7-year-old daughter how to dance. Recently, has spearheaded an ambitious KT boundary project where over 100 years of collective research, ranging from pollen to plants to vertebrates, will all be integrated into one data set and used to answer questions regarding the tempo of both the extinction event and the subsequent recovery. And for Ian Miller, he was raised nearly feral in rural Washington state and first discovered geology and paleontology while scavenging mine tailings for fool's gold and pulling Miocene clams out of road cuts. Ian attended the Colorado College as an undergraduate and did his first paleobotanical work at the Denver Museum of Nature and Science with then curator Kirk Johnson. After a 2-year stint as a field geologist with a New Mexico geotechnical and engineering firm, Ian felt the academic siren's call and headed off to Yale University, where he studied paleobotany and tectonics and earned himself the title of a tectonobotanist. Ian returned to Denver and is now curator of paleobotany and the director of Earth and Space Sciences at the Denver Museum of Nature and Science. Beyond his work as a scientist, Ian also leads an ongoing major initiative at the Denver Museum, the Colorado Experience. This initiative aims to deepen our community's connection with science and the natural world. When not digging for fossils or scheming new quarries, Ian can be found fishing, skiing, or hiking Colorado's mountains with his wife, Robin, and his perpetually happy dog, Wilson. So with that, Tyler and Ian, thank you both very much for being here. And I will join back in at the end of the talk to help with some questions. So thank you, guys.
Oh, well, thank you so much. And I'm glad you went with the fun bios. That was that gave us both a pretty good chuckle. Which was fun. So we are absolutely thrilled to be here today, and it's so exciting to be able to present this information to RMAG and to see so many familiar faces and names pop up. We miss all of you, and we hope to see you soon again. And thank you so much for everything you do for the geological community. And so again, it's just really a thrill for us to be able to share this local story of discovery and of really cool science that's still unfolding right here in our backyards. So to put this in some perspective, here's a sort of simplified diagram of the diversity of life over the last 600 million years. This is diversity of multicellular life on Earth. And there's time along the bottom from about 600 million to the present day. And then our proxy for diversity is there on the Y column, and it's just the number of families. And as you go from left to right, you can see diversity changing through time. The big color blocks are just sort of these big groupings that paleontologists use to talk about different ages of fauna and flora. But the most important feature of this is that you see diversification from 600 million years ago to the present day, and yet there's a lot of structure in that graph. And the most important structure I want you to notice are those sawtooth patterns. Anytime you see a big drop in that diagram, and those are the great mass extinctions in Earth's history, the extinction of at least 50% of the species on Earth. And we see a big drop, 5 of them, the most recent of which is the end Cretaceous 66 million years ago. So when you think of an extinction, I want you to think about it in a couple of different ways, and this will become important as we talk through, or we go through this talk. This is just a schematic diagram with pre-extinction time there on the left, post-extinction time on the right, and what you see is a branching tree of life going into that red line. And that branching tree could be diversity of species, or at any level, could it be families, so on and so forth. It could also be lifestyles. You can think of that as a branching tree of different kinds of lifestyles. There's an extinction event, and a few things make it through. And so you could think of that extinction not only as we often do, of all the things we lost, but also as an incredible filter. And then, importantly, in the time afterwards, a period of origins. And that's that blue box, where the few things that make it through then inhabit a world in which there's very little competition and evolve rapidly and diversify rapidly. So when we look back at the last great mass extinction in Earth's history, the Cretaceous-Paleogene, or the end Cretaceous mass extinction, we lost all the dinosaurs. But it is this moment of diversification. So when you look out the window today, you see all these incredible animals and everything, and plants and insects, and everything you see outside today had an ancestor that had to survive the world's last great mass extinction. So here we go, with birds and plants, insects and lions and tigers, and the list goes on. Everything outside your window right now had to survive Earth's last great mass extinction. And so that moment after the mass extinction is essentially the origin of our own modern world. So what happened? You guys probably all know this story. We know that we got smacked by a giant space rock moving at something like 150,000 kilometers an hour. It hit what is now the Yucatan Peninsula, and it pulled outer space right to the surface of the planet. And this asteroid, which was on the order of 10 kilometers across, blew a hole in the ground some 20 kilometers deep. And it sent a shockwave and firestorm from Mexico to Alaska in just mere moments, probably about 5 minutes. You can have the next slide, Tyler. So here's our picture of our little location here in Denver, Colorado, with two of the iconic dinosaurs at the time, Tyrannosaurus rex and Triceratops, both of which we found right here in the sediments in our backyard. And Tyler and I always think this is a funny sort of diagram, beautiful diagram or painting from the National Geographic, but of course those two dinosaurs seem to be preoccupied with each other instead of that giant fireball and shockwave coming at them. But suffice it to say, if you were in that blast wave, you would have been liquefied and incinerated just a couple of minutes after impact. So at the same time, it's quite remarkable, at the same time we get smacked by this giant space rock over in the Yucatan Peninsula, and we can talk at greater length about its myriad of environmental effects. But at the same time, there's these gigantic flood basalts erupting in India, and you've probably heard of them. They're called the Deccan Traps. And there's a bit of a push and pull of those people who really feel that the Deccan Traps were important in the extinction, and those who feel that the impact or the meteor was more important. And we can talk about that later as well too. But suffice it to say, there is a remarkable amount of material that was extruded during these flood basalts in what is now Western India. And here's just the incised valleys on the edge of what's called the Western Ghats, this massive plateau in Western India that preserves at least the on-land portion of these basalt flows. And that's several thousand feet of elevation. You can see the stacked up flows. These are second only to the Siberian Traps, which were erupted about 250 million years ago, and associated with a great extinction as well. But much of these are underwater. But again, these two things working together, conspiring, we believe, led to the extinction of the dinosaurs. And so this is a fun diagram here showing our Triceratops now as a skeleton and a few of the critters that made it through crawling over its skeleton. So Tyler, as you'll hear, grew up in North Dakota, and as you heard during his bio, in North Dakota. And this is actually his backyard from a NOVA special that came out right when he showed up at the museum. And those are teams of people digging dinosaurs. And what you're looking at is the sediments of the Hell Creek Formation on the bottom and the Fort Union on the top. And that line, that horizontal line, is the KT boundary, or the KPG boundary, 66 million years ago, and it marks the it is the layer that records the asteroid impact in Mexico. And those ghostly figures on the bottom are all the dinosaurs you find in those sediments. And above that line, we have never found anywhere on Earth an articulated dinosaur. And in fact, the fossils above that line in the tens to hundreds of thousands of years after the extinction are really quite rare. So I'm going to take you now a little closer to home. Tyler and I, Tyler joined the museum about 5 years ago now, a little bit more than 5 years ago, and he and I are both worked a lot on the end of the Cretaceous, the extinction of everything at that moment when the meteor hit. But he and I sort of teamed up thinking, where could we go to sort of make a big discovery and a splash around what life was like after the extinction? What did that recovery look like? Because very little information had been known. So we've been working the Denver Basin for a long time, myself and Kirk Johnson before me. And what you see here now is a shaded relief map of Colorado and the Cretaceous and the Paleogene sediments in the Denver Basin, with, of course, Denver and Colorado Springs noted. In fact, this is actually the Denver-Julesburg Basin, for those of you who are probably very familiar with it. And so here's just a very schematic cross-section, just now showing what we would term the laramide sediments cutting through the basin there, or slicing across the Front Range through the basin for a cross-section here. And this is the incredible work of Bob Reynolds and associates Marika Deschen at the USGS now. They really pulled this story together really right before I showed up at the museum about 15 years ago. And so this is based on their work. And they use a number of techniques to do this. I'll hit the next slide here, Tyler. So there are 2 cored wells, continuously cored wells in the basin. One that the USGS, I think the USGS cored it near Castle Pines, Colorado. It was cored about 40 years ago. And then another cored by the museum about 20 years ago out near the town of Kiowa. And so these 2 cores give us a mountain proximal and a sort of basin central perspective, stratigraphic perspective of the basin. And we've added to that actually more now than 4,000 oil, gas, and water well logs to understand the subsurface of the basin. And one of the reasons we do this is because the basin is very poorly outcropped. And so we need to be able to project layers through the subsurface. In this map here, red is gas, water is blue, and then the oil are black dots. So here's just a little model. This is all Marika Deschen and her work. She's at the USGS now, and she in GIS, and this is actually a figure for about a decade ago, was able to model the subsurface of the basin and be able to predict the age of outcrops at the surface based on this kind of work. And through that, we've been able to do some pretty remarkable things. This is now Google Earth with a bunch of fossil leaf sites on it. And this is down in Colorado Springs, just going up one of the arroyos that moves through the northern part of the city. And you can see all the sites there. And if we zoom in one more time, now we're looking at the backyard, and we see Cretaceous green sites and then sort of a tan or a brown Paleogene site, and the model predicting the location of the KPG boundary going right between those 2 sites. Pretty remarkable. So you can use this tool actually to find out the age of the rocks, the age of the rocks below the alluvium in your backyard, if you're curious. So all of this together brought to bear this incredible record of laramide sediments here on the Front Range in the Denver Basin. And if we hit the slide one more time, well, just a couple key features pull up here. So Denver and Castle Rock and Colorado Springs, and if you hit it one more time, Tyler, we have the KT boundary. And so just to, again, orient you a little bit, the lightest green is here, shale. We have the Fox Hills above that, Laramie in green, and then this cinerogenic laramide package of the Denver and the darker brown, and then the Dawson and the lighter brown. And the highest elevation here is right there, sort of down in the bottom, in the middle of the Dawson, the Palmer Divide. And so the KT boundary sits right in the middle of this basin. It's an incredible record of this time period. Okay, next slide. And one of the more recent pieces of work that have come out of the basin is that since we have the laramide going off and there's this incredible mantle of volcanoes on it, they're belching ashes. And in the distal parts of the basin where we get a lot of lignite, we get an incredible record of volcanic ashes, which are easily dated, typically easily dated using either uranium lead or argon dating. And so here's one of our collaborators from the Smithsonian, Rich Barkley, pointing to the pollen calibrated KPG boundary, which we know to within a few centimeters, and beautiful ash beds above and below it. And with this work, we've been able to date the KT boundary to about 66.021 million years, very, very precisely. Okay, So that's a little bit about the geology in the Denver area, or the Denver Basin. But all of this is just to say, we went from this incredible ecosystem. This is the moment before the impact, if you will. Everything in here is based on a fossil leaf or vertebrate that we found. These are two dinosaurs that Tyler actually named, called Anzu Wiley-eye, the chicken from hell. This guy, and this just represents this incredible ecosystem and life before the asteroid impact. And right afterwards, we have a very depauperate world in which diversity of plants and animals is very low, and this world's trying to recover from this incredible event that happened in our history, which essentially is the last great mass extinction in Earth's history. Okay, next slide. Okay, so back to the Denver Basin. We're going to take you down to the south, and if you hit the slide one more time, Tyler, to an area called Corral Bluffs, just to the east of Colorado Springs. Okay, one more slide, I think. So here is Corral Bluffs. This is a view looking west from the eastern edge of the bluffs towards Pikes Peak. And if you were able to go right over that rise there before the rain clouds, you would be in Colorado Springs, in downtown Colorado Springs. And in fact, Corral Bluffs is incorporated Colorado Springs. It's pretty incredible. So Tyler and I we're very interested in sort of making contributing to this idea of how did the modern world start? And to do that, you've got to look after that last great mass extinction. And we rolled out the geologic maps when we sort of teamed up on this idea. And we thought we were going to make a discovery probably in some far-flung place. But again, you go to your backyard first, and North America, and particularly our neck of the woods, has a great record of the end Cretaceous and beginning of the Paleogene. And so we went down to Colorado Springs and to Corral Bluffs to see if we could see something that people hadn't seen in the many decades before we arrived there. So with that, I think I'm going to hand it over to Tyler to pick up the story.
Great, thanks, Ian. Yeah, like Ian said, we really wanted to contribute to this story, and that is the story of recovery after Earth's last mass extinction. I grew up in North Dakota, as Ian and Dan said, and earliest childhood memories out looking for fossils, but always the Earth's last dinosaur ecosystem fossils. And so I grew up thinking about this extinction, working with folks like Kirk Johnson and others, who are really pushing that question forward of what was the cause of the mass extinction. But we have a really good understanding of what caused that mass extinction. And what we don't really know a lot about is what happened afterwards. And again, having grown up in North Dakota, I remember finding all these fossils below the boundary, going above the KPG boundary and not finding anything. And always just being fascinated by that and just thinking, man, if we could find fossils from this interval of time, that would be an incredible story. We don't know what that story is because it hasn't been told. So Corral Bluffs is not, let's see, oh, there we go. Corral Bluffs is not a new area by any stretch of the imagination, right? People have been going out to Corral Bluffs for at least the last 100 years. So here's a picture from Roland Brown's expedition in the 1940s, 1930s really. And they noted dinosaurs at the bottom of the hill. They noted mammals higher up in the hill. They knew there was a mass extinction somewhere in there. But just like other scientists, they were not impressed by the area of the outcrop, nor by the fossils. The area is pretty small. The whole area is only about maybe 24 square kilometers, and of that, only a much smaller of that subset of that actually has outcrop. So they went further south. Most paleontologists went further south into the San Juan Basin, where they made incredible discoveries from roughly this interval of time. So our own museum has even been working at Corral Bluffs for at least the last 40 years or so. But we went down there in 2016, and initially we weren't finding a whole lot. I was very underwhelmed with what I was seeing. Did get pretty excited by this find here. This is typically what you find from this interval of time. This is a really good find prior to this discovery. And what you're looking at here are two mammal jaws. There's the lower part of the jaw, and then you can see the teeth sticking up. And again, prior to this discovery, I can count on one hand how many mammal jaws, or really mammal fossils, that I had found in over 25 years of looking from this interval of time. But anyway, I thought, you know, there was a few clues that suggested that there might be more to this area at Crowell Bluffs. And one of those clues was the discovery of this really nice palate of a mammal jaw, or of a mammal called Carciopticus. And this was made by one of our volunteers, Sharon Melito, several years ago. And so I remember seeing this in the collection and thinking, wow, that's a really complete fossil. You know, and of course, where there's one, why isn't there two? Why wouldn't there be more great fossils out there? But we weren't finding a whole lot. And I also started to think about some of my other fossil finding experiences, particularly in South Africa. I work on the origin of turtles and another different scientific problem down there. And down there, their search image is very different than our search image here, or at least the way I was trained as a vertebrate paleontologist. As a vertebrate paleontologist, we look for, at least on terrestrial environments, we look for bone, we follow the bone trail. If we're lucky, there'll be a bone sticking out of the side of the hill, and that's where we dig. Pretty simple. There, rather than searching for bits of bone, they look for concretions. And so I thought, well, maybe the fossils are sort of hiding in these concretions, right? Why not? Worth a shot. And I remember picking up this sort of ugly, nondescript white rock and taking my rock hammer there and cracking it open. And there staring back at me was a mostly complete mammal skull. So you can see maybe the top of the skull right here. You kind of squint, there's a couple of teeth right here as well as over here. I cut the mammal skull right in cross section, right through the brain. And it was a remarkable moment because I called Ian over, I called Sharon over, and I showed them what I found, and we were just, you know, just giggling. We were so excited because we'd never seen a mammal fossil this complete from this interval of time. And, you know, I was busily tending to my fossil, and Ian goes around the corner and comes carrying back a complete mammal skull. Sharon goes around the corner and comes back carrying a complete mammal skull. Within a matter of minutes, we had found maybe 5 or 6 mammal skulls from an interval time where we really only had teeth, or, and if you're lucky, jaws. It was amazing. So here you can see, you know, what these concretions look like, and then here you can see what's inside of these concretions. In this case, this is a really bizarre mammal called Eoconodon. And everybody here knows what a concretion is. It's just a special type of rock that forms around an organic nucleus. Think of like a pearl in an oyster shell. And what's unusual about these concretions is that these concretions are phosphatic. This is a question that I'm not going to get into too much. We have our ace geologist listening in right now, James Hagedorn, and this is something that he's currently actively working on. But why do we have all of these phosphatic concretions in a terrestrial environment? Very, very unusual. So here's just another example of what the concretions look like when we find them. You can see why paleontologists have been walking over these concretions for years, because they just don't look like an awful lot. They're pretty ugly, they're pretty nondescript, but you can see after hundreds of hours of mechanical preparation of these, as well as air abrasion, preparation of the fossils, you can see we're able to extract the fossils one by one. Here's another example. This is one of my favorites. This is a new species of turtle that Ian and I are currently working on right now. I just sort of love like the Darth Vader look of this particular animal. But we're just uncovering a whole ecosystem inside of these ugly, ugly, nondescript looking concretions. So here you can see what they look like. Some of them you can kind of get clues as to what's inside, but others it's pretty difficult to determine. But after many, many hours of preparation, we're finding complete skulls, in some cases complete skeletons, whole turtle shells, just hundreds of these concretions. We're still going out now. I was out last week finding more beautiful mammals, turtles, and crocodiles. This is just a small subset of some of the vertebrates that we found from this interval of time. And it's just remarkable, because in this picture, we have new species of mammals, new species of turtles, new species of crocodilians. And if it's not a new species or new to science, it's the most complete specimen known of a known taxon or a known species. So we're gaining new knowledge either way. We're really, and Ian's going to talk about this here now, we're really able to bring these animals back to life, unlike we've ever been able to do before, because we went from having teeth and jaws to now having at least complete skulls of these animals. And in addition to the amazing vertebrate record, we have an equally amazing plant record. And with that, I'll hand it back over to Ian, the paleobotanist on the team.
So we beyond just the two of us, we have this remarkable team of people now associated with this project, and it actually numbers probably more than 50 internationally. And there's actually a team of paleobotanists. My specialty is fossil plants, and we have 5 paleobotanists on the team. That's about 5 to 7% of all paleobotanists in the world working together on one thing, which is remarkable. But our job was really to flesh out the fossil plant or the forest story, if you will, of this project, to go along with this incredible vertebrate find. So on the left-hand side there, you can see some impressions of fossil leaves. We'll talk about a few of those, and Tyler will mention later on how you can use those to actually tell temperature. You can imagine plants are attuned to their local temperature, and we can actually back out temperature. But they also tell us a lot about the diversity of those forests and who recovered and when they came back. On the right-hand side are 3 pollen slides, and some of you probably have actually looked at pollen before. That's not usually the case, fossil pollen that is. That's not usually the case when we're giving a talk on these topics. But on the bottom there you can see a typical Cretaceous pollinophora or pollen flora, if you will. And you can see all the little tiny Ks next to everything. Those are Cretaceous-only taxa. Between A and B, we have the asteroid impact and the extinction of the dinosaurs, and we see a commensurate extinction in the plants, probably about 60% of the species. And one of the features of the recovery, the very earliest part of the recovery, now we're only talking a few hundreds to maybe 1,000 years, is a great proliferation of ferns. And so you see all these fern spores there, those little trilete ferns, a little F next to them. And then eventually you see the world come back with a new pollinophora, now some hundreds of thousands of years later. And this is just another way of looking at the forest through its pollen grains. Next slide. So Tyler talked a little bit about the mechanical preparation. Here's a beautiful skull of a small mammal coming out of the rock, and it takes actually these incredible people who work around. They're all remote, and the precision required to get these things out of the rock is unbelievable. And so these guys are working in their basements in Chicago with their cats and things like that, and we keep mailing them things, and then undescript rocks, and it comes back with this incredible one-of-a-kind fossil. So that's one way to sort of pull this information out of these concretions. But another way to do it, and this has really been revolutionary in paleontology in the last 2 decades, is we're able to peer inside the fossils. And we do this with computed tomography, basically a series of stacked x-rays. And here's the CT scanner at Wheat Ridge Veterinary Hospital on about 11 p.m. on a Friday night. And Tyler we're sending a fossil jacket in plaster with fossils inside it through what probably was used for dogs and cats all day long. And just as an aside, you guys are all graced with a bit of a paleontological celebrity, James Hagedorn, who's on this this call, now identifying himself as the late great Dolph Seilacher. He really is one of the few people who developed the science and changed the way we are able to peer inside these fossils. So just to show you a little bit of this kind of data, we'll go to the next slide. Here's the grayed out is a skull, a very partial skull. It's missing its nose. It's broken off right there at its face. The top and bottom are the zygomorphic arches, basically the edges of the eyeballs. So Tyler's highlighting the eyeball holes. But what you see in color there is the endocast of the brain in teal, and then in purple, we actually see the ears, and we're going to blow that up here. And this next one. So now we've just pulled out the brain and the ears of this guy, and this is actually a pretty low resolution scan. They get much, much better than this, but this is a quick scan, so you can see the X-ray slices. But a couple of things we're able to tell right away. So there's a proxy for encephalization quotient, basically how big your brain is compared to your head and body. And this guy we know is not very intelligent. We can say something about their agility and where they're living based on their ears and the shape of those little loopy things. Those are the semicircular canals for the ears. And this guy gets an agility score that suggests that he's very slow moving. And yet at the front there, the brain is about 10% nose neural tissue, basically the olfactory bulbs. We know this guy had incredible sense of smell based on that size. So you can now start to paint a picture with this kind of data of the kind of animal, what it was doing afterwards. This guy didn't have to run away from dinosaurs or anything like that, but did need a great sense of smell to find food probably on the forest floor. So this whole discovery and this whole project has been sort of graced with amazing finds. And so one of the things that Tyler and I do, and he actually runs this program right now at the museum, is we work with teens during the summers. And this happens across the sciences and across the disciplines. And we take about 20 teens who are often first in their family to intend to go to college and have a great passion for science. And this is their chance as 14 and 15-year-olds to get involved in real science. And so in 2017, Tyler and I had 8 of these teens, and this one right here, this is Aeon Way Smith. She's now pursuing medical school, but she was one of our 8 teens that summer, and she was in a fossil leaf quarry with me. And on the left there, you see a guy filming us in the quarry. We have as Tyler will share later, a nice documentary on this project. And they came along with us the entire time, right after the discovery was made, just a few days after they joined the teams. So Aeon, being sharp, she was very shy and quiet, but being very sharp, she was listening to us debate, what were the things that were driving these evolution of these mammals in the hundreds of thousands of years after the extinction of the dinosaur? What was driving their evolution, their diversification, how their ecologies were changing and specializing? And we thought the answer had to be in part due to the changing plants. And one of the things that's been hypothesized for a long time is that fossil legumes or fossil beans evolved at this moment, but it was just inferred. So you can infer the evolution, the start of these groups based on their modern diversity. And while nobody had found a fossil of this age, we knew they should be there. And so Tyler was pushing us to make predictions around this, and we had found some hints that maybe something like this, we found a little chunk of a leaf or something like that. Legumes could be around at this time, but we were pushing back saying, well, if you're gonna find a legume, you have to find a bean pod. And so Aeon was digging fossil leaves alongside me, and there's other people in the background you can't see, cracking open rocks. And she had been carefully listening, and during the middle of an interview, she started pulling my shirt and said, look at this, look at this. And at first glance, it just looked like a stick, and then it caught the light, and this thing was a bean pod. So if we go to the next slide, Aeon had found the world's oldest bean pod anywhere on the planet. And beans are incredibly important. So today, they're second only to grains in terms of a food source to humanity and life on Earth, vertebrate life on Earth, terrestrial vertebrate life on Earth. And they are the 3rd most speciose or diverse group of plants There's more than 20,000 species of them on the planet today. In the tropics, they're an incredibly important source of lumber. There are more than 10,000 legume trees in the tropics. Even though we think of legumes as the green beans at the end of the table, they're a remarkable part of the world's forest. And Aeon had found the earliest legume pod anywhere on the planet. And so there's a legume just to show you a part and counterpart of one split open, and then the tiny, tiny leaves that go alongside it. So this thing was sort of like the locusts we see here in Denver today. So here's just a fun little reconstruction of what this thing might have looked like. And we're working this up right now. And it's all due to Aeon, who was at the time 14 and found the earliest legume pod. Now we've got about 50 of these things in our collections. So before I hand it back to Tyler, I just want to drive home this point of what was available to us at this discovery. And I think probably as the geologists in this talk know, it's pretty unusual to be able to find all aspects of the sort of fossil record and have the ability to date the rocks. So if you're finding plants, you're often not finding vertebrates because of the sort of preservation potential of plants versus vertebrates, and vice versa. And it gets down to the chemistry of the sediments and so on and so forth, and just the depositional environments. But again, the window into the vertebrates was very special. It's these phosphate concretions preserving the skulls of the vertebrates, which clearly had something to do with it. And then at any given time in the rock record, if you're able to have both animals and plants at that section, you'd be thrilled. But then to be able to add time to it is yet a whole nother aspect. And as you probably also know, it's quite difficult to precisely date rocks. And many rocks are not amenable to dating, and yet these rocks were through magnetostratigraphy and uranium-lead high-resolution dating of volcanic ashes. And so we sort of call this the trifecta of paleontology. And then finally, just not to put too fine a point on it, if you have every three parts of that triangle at any point in the rock record, you would be thrilled, and it would be a veritable treasure trove of data for you to work on. And yet to have it in this moment, right after the end of the time of the dinosaurs, where we've virtually had no data beforehand to tell this incredible story of now the recovery of life after the last great mass extinction, and to be able to time it. So we have this trifecta of paleontology. So Tyler's going to pull this thing together and share some of the real highlights of the discovery so far. And yeah, you'll take us to the finish line.
Great, thanks, Ian. Let's see. So, like I said before, like Ian said, we knew there would be a big story if we could find fossils. So now we have the fossils, we have the vertebrates, we have the plants. So what is that story? Well, this is what we knew before. Of course, we knew there was a mass extinction caused by the asteroid that struck Earth that wiped out the dinosaurs. And then what happened afterwards was sort of a blank slate. We didn't know an awful lot. The first thing that we needed to do was to map out all the rocks and then place all of our fossils in the stratigraphic column. And like Ian said, of course, he and I get to give this presentation and get the glory, if you will. But there were so many important scientists involved and contributed a huge amount of work to this particular project. There were 16 scientists on our initial publication. And one of the key scientists was Ken Weissenberger here. And he was our ace stratigrapher who mapped out all the rocks. And, with all of his data, we were really able to place our hundreds or almost close to 1,000 localities into a stratigraphic column. And the next thing we needed to do was to date those rocks. And we did, we used a number of techniques. We dated one volcanic ash bed, but the real key way in which we were able to infer time was using the paleomagnetics. And that was the work of Will Clyde and his student Anthony Fontes here, who did his master's thesis on this particular project. And so they were able to, we punched in, I think, 8 different PMEG sections along the entire transect of Corral Bluffs. So we were really able to very precisely, with their data and Ken's data, precisely place in all of our vertebrates and our plants in time. And so what did we know? What did those data show? Well, we knew based on that we had the first 1 million years after the mass extinction. So I put this down at 0 because, this really is the biologic reset button, going from the age of the reptiles to the age of the mammals. Then the next thing, of course, we're finding all of these amazingly complete vertebrate fossils. Here are just some of the skulls, as well as the associated artwork of some of the animals that we're finding. And we're really just beginning a lot of this work right now. CT scanning them, pulling out their brains and their ears, and looking at various isotopes to figure out what they were eating and where they were living. But with this study, one of the easiest things to do, now that you have whole skulls rather than just teeth or jaws, is to look at body size. How big were these mammals? Body mass impacts pretty much all aspects of an animal's ecology. Where it can live, what it eats. So that's the first thing that we decided to do with this data set, was look at maximum mammalian body mass. When were the biggest mammals on the landscape? And so here we go in orange. Sorry, it's in pounds here. We've changed that, I guess, for other audiences. But anyway, the largest mammal down in the Cretaceous is about 8 to 10 kilograms or so, roughly the size of a small raccoon. The largest mammal to survive the mass extinction is about 0.5 kilogram, about the size of a rat. And then we see 2 really big jumps in body size, here at 300,000 years after the mass extinction, and then again at 700,000 years after the mass extinction. And with these in mind, this is why I was pushing Ian and the paleobotanist to tell me what was going on with the forest ecology. These animals aren't evolving in isolation. There's something that's driving this increase in body size, in addition to just time. At least that was our hypothesis. So what was going on with the forests at the time? And so that's where Ian and his team really stepped up big. You're collecting over, I think, over 77 plant localities. We had Anton Berkovici, who was our palynologist, who counted literally several 100,000 grains of pollen to look at relative abundance of pollen through time. So it was a huge effort on both of their parts. And one of the first things that we've noted is the fern spike. Obviously, we're not the first to note that. This is a phenomenon that we see around the world, where you get a proliferation of ferns right after the mass extinction. And that's something that we see right here. So here's the distribution of fern pollen, and then down here, the percentage on each of those pollen slides. So we've dubbed this the fern world. The next thing that we noticed using both pollen as well as the megafloral plants was a proliferation of palms, at least in our research area. We don't know if this is, can be extrapolated to other research areas, but at least at Corral Bluffs, in this mountain proximal environment, there was a proliferation of palm trees for roughly 300,000 years after the mass extinction. You can see at some of these, there's almost 100% of the palm, or 100% of the pollen is made up of palms. So just an abundance of palms, which we've dubbed the palm world. And we saw that in the pollen record, as you can see down here, as well as the abundance of palm fronds, flowers, as well as many in situ and other palm tree trunks. Then the next thing that we noticed with the overall forest ecology was the forests were starting to come back in terms of diversity. And one of the main groups that comes back is the Juglandaceous pollen, which belongs to the walnut family. This is what that pollen looks like. It's one of the key groups to identify pollen biozones. It's walnut pollen. Many of you probably are much more familiar with it than I am, but we've dubbed this the pecan pie world because pecans are part of walnuts. And right when we see the forest jumping back in diversity, partly by the increase in diversification of the Juglandaceous pollen, we get a big jump in body size. So that first big jump at 300,000 years is a correlation between forest recovery, the walnut family or pecan pie, and then this jump in body size. And then the last thing that we see at 700,000 years, again, an amazing correlation between Aeon's legume and this giant jump in body size right here. They're found at almost the exact same stratigraphic level. And of course, legumes are loaded with protein, so we jokingly started calling this the protein bar world. So, you know, at the same moment of the plants, you get this big jump in body size in the animals at 700,000 years after the mass extinction. And then this is, you know, really Ian's world here, but among modern ecosystems, there's a correlation between the number of plants on the landscape that have a toothed margin versus the number of plants on the landscape that have a smooth edged margin. And this correlates very well with temperature, of course, making it a powerful tool for inferring paleo temperature. So something that I know all of you guys are familiar with, but this is one of our key ways in which we infer paleo temperature from this stratigraphic interval. And one of the cool things that we noted was there were 3 distinct warming intervals in our research area. One here at about 100,000 years, 400,000 years after the mass extinction, another at 300,000 years, which lines up with the pecan pie world, which also lines up with this increase in body size. And then again, one that we're a little more tentative with, but we see another one at 700,000 years with the appearance of the oldest legume, as well as this big jump in body size here. So we sort of had it all, you know, at least we thought, you know, we had paleo temperature. With the changing in the paleo temperature, there's an impact with the forests. With the changing forest ecology, that's having an impact on the evolution of these early placental mammals. And then, of course, we could put this amazing timeline next to it to really figure out when, not only how, but when a lot of these major changes were occurring in that first 1 million years after the mass extinction. So we've worked with a paleo artist now from Siberia to reconstruct these landscapes. And so a lot of work goes in among all of the scientists to thoroughly vet the facies, the plants, and the animals. And so I think it's a great way to visualize how these landscapes were changing during this interval of time. So this is what Colorado would have looked like just over 66 million years ago. You know, lots of feathered dinosaurs, lots of rivers, big T-Rex roaming across the landscape. And of course, the single worst day for multicellular life on Earth, the giant asteroid strikes, the biologic reset button, going from the age of the dinosaurs to reptiles to the age of the mammals. And now we're able to, you know, with this fossil record, really able to tell that story of what happened next. And so this is what Colorado would have looked like right after that mass extinction. You know, the world would have been blanketed in ferns. You have the Rocky Mountains in the distance. And then here I've chosen to put the largest mammal that survived the mass extinction. This is a mammal called Mesodma. Again, about the size of a good New York subway rat, about a ½ kilogram, next to the largest terrestrial vertebrate that survived the mass extinction. And that's a big soft-shell turtle called Extinction that would have weighed several hundred pounds. And then within, you know, for the first really 300,000 years after the mass extinction, the forests are starting to come back in terms of diversity, but they were really patchy and they were really dominated by palms. But in this palm-dominated forest, the mammals start to come back. I should say that about 90% of mammals go extinct at the KPG boundary, so they get hit really hard, but they bounce back quickly. So within 100,000 years, excuse me, you have mammals like this mammal right here, that's just about as big as mammals before the mass extinction, you know, 10-ish or so kilograms. They come back in terms of body size. They're also coming back in terms of diversity. And then at 300,000 years after the mass extinction, big things are happening. Forests are really starting to come back. The jugandaceous pollen, or the walnut family of life, is coming back, as you can see right here. So this is that pecan pie moment. And in that exact moment, we get mammals that I should say are herbivorous, or plant eaters, that are appearing on the landscape that are 30 times larger than the mammals that survived the mass extinction. So much, much larger. And then finally, at 700,000 years, the ecosystem's continuing to come back. The forests are diversifying. One of the key groups that we see appearing at this interval of time, of course, are the legumes. So this is reconstruction of what the legumes would have looked like. We hypothesize that some of these large mammals were likely eating these new protein-rich food sources. And at this interval, at 700,000 years, we get the oldest legume, and we get the largest mammal from our data set appearing on the landscape at 700,000 years after the mass extinction. And this is a mammal that's about the size of a small wolf, maybe 70-ish, 60, 70-ish kilograms. And this is an animal that is 100 times larger than the largest mammal that survives the mass extinction. 100 times larger within 700,000 years. A comparable jump in body size won't occur for another 30 million years. So all of this, I think, at least to me, speaks to how quickly the ecosystem bounced back after that mass extinction. 700,000 years is not that long to have a really rich diversity of plants, as well as animals, and animals that are much, much bigger than they ever were during the age of the dinosaurs, with the mammals, that is. The mammals are bigger now than at this interval than during the age of the dinosaurs. So, with that, I mean, Ian and I always joke about these trifectas, and it was another trifecta that was just really an amazing dream for a lot of us, where we were able to publish this discovery in Science. Like I said, there were 16 scientists involved in this. At the same time, we were able to work with the Howard Hughes Medical Institute to create a 1-hour NOVA special called The Rise of the Mammals, which if you haven't seen it, you should go check it out. Over the upcoming holidays. You can stream it for free. And then finally, we were able to work with some museum professionals at our own museum, the Denver Museum of Nature and Science, to put together this exhibit called After the Asteroid. And it's a really cool exhibit where we highlight some of the best fossils that we found from this interval of time. And they're on display now. So if you have the opportunity, you can come in to the museum and check them out. Now. And with that, I think I would like to just end with it's about a 1 minute or so, I know we're running short of time, but 1 minute clip, sort of a highlight reel of the documentary, which I think does a really nice job of just sort of summarizing the excitement of discovery of this particular find. So here goes, see if this works. It's a really bad time for life on Earth.
I mean, you could go your entire career and not find a skull this time period. That's how rare they are.
They're excruciatingly hard to find.
There's just nothing like picking up something and finding out it's something amazing.
It was crazy the way it happened.
Bam, we hit it big. I just found a mammal skull.
It was like opening a door into a new world.
We want to build up a picture of how life evolved at this period.
Some things survive, right? Including some of our earliest ancestors.
Over the the last 66 million years. Mammals evolved an incredible diversity of forms.
That moment of rapid mammal evolution is effectively the trigger to our existence here on planet Earth.
All right. Well, thanks everybody for tuning in, and sorry we went a little long there, but appreciate it. If there is time, I think Ian and I would be happy to entertain any questions that folks might have.
Yeah, guys, really, thank you both so much. Both Ian and Tyler and James being on the line and all of your team. This is really, really cool. So Ian and Tyler have both said that they're willing to stick around for a little while to answer some questions. Ian, you've been doing an awesome job keeping up with questions. There's still some stuff coming out there. I want to remind everybody just really quick, this is our last talk of the year. Please join us in January. Stick around right now for some questions if you'd like to. And also the original plan was that Ian and Tyler were actually going to take out a group of RMAG geologists to Corral Bluffs this year. But then, you know, with COVID restrictions, we are still hoping to plan a trip next year at some point in the summer. So actually, you know, guys, if you don't mind, I'll kick it off with my own question. Something that might be relevant for me, and I'm assuming other people might be thinking the same thing. Do you need volunteers to come and carry concretions and rocks out of there?
Absolutely. And we need your big brains to help, help solve a lot of these geological questions that we have. You know, James has been spearheading a lot of those. But I mean, we go out there and we're still going out there. We're finding amazing fossils every time we go out. I'm still just blown away. I think I found all the fossils. I've said that at least 5 different times. And every time I go out there, I find yet another amazing thing, another amazing fossil. So we have big plans to go out and do more field work. And yes, we could always use more volunteers to help collect the fossils, but in all seriousness, it would also be great just to get other people out there and thinking about just things that we're not even thinking about, you know, just to see the rocks. And you know, it was really too bad that we weren't able to do that field trip that we were planning. COVID ruins everything. So, but in the future, we're looking forward to doing it in the future and to getting a lot of folks out there. That would be amazing.
Wonderful. Well, I got your emails, so I'm definitely going to use it.
Awesome.
So Ian's been keeping up with questions here. I'm trying to go through some of the questions that may or may not have been answered. Any carnivores from the intervals you studied? Have you found any carnivores?
So no pure carnivore, no animal that is related to dogs and cats in the sense of it being, you know, carnivorous. There are meat-eating mammals out on the landscape, though. So, you know, there's a difference between, I guess, ecology and evolution or phylogeny. So they evolved in this interval of time. I mean, the thing is with all mammals, all placental mammals, I should say, there was just an absolute explosion in the diversification. They just took off. So our own group of primates, our own group even can be traced all the way back into this earliest interval in the form of Plesiadapiforms, a different group of mammal, but closely related to primates. And we also think that there very well could be some carnivores. The problem is that you get a rapid diversification, and you combine that in deep time and a poor fossil record, then trying to figure out whether something is a mammal, is a carnivore versus a hoofed mammal or some other type of mammal is really, really, really difficult. But that is exactly what we're trying to figure out right now, is trying to unravel that phylogenetic knot that exists at the base of placental mammals. That's going to take some time, though.
Yeah, thank you. There's an interesting question here from Rebecca that's kind of cool. Any thoughts on the theory that mammal proliferation had to do with our ability to fend off fungi better than reptiles?
Yeah, so this has come up a couple of different times, and it is a really interesting question. We actually had a specialist in infectious fungi from Johns Hopkins reached out to us recently, and in fact, we owe him a response. And the idea is that in these sort of post-extinction worlds, it's really well known for the Permian Triassic that there's a proliferation of fungi. And we actually see their spores and hyphae hyper-represented in the rock record, sort of like the fern spore spike. And there's this idea, well, it's known that mammals do really, really well or can fend off these fungal infections better than other groups of animals. But there's a couple of issues. One, we don't necessarily have the time resolution to be able to investigate that. We're now talking down to decades to maybe hundreds of years after the boundary. Also, birds do incredibly well after this boundary. And in fact, birds are the most diverse group of terrestrial vertebrates on land. We, of course, see the world through the mammal eyes, but the birds may be the biggest winners, at least from a diversity standpoint. One of the thoughts is that temperature, body temperature, may have something to do with it. But again, the birds are warm-blooded, as are the dinosaurs. Many of the dinosaurs are warm-blooded. So I don't know. I've really got to think about it a little bit more. I don't know if Tyler, if you want to speculate on that at all, but I think it's one of those things that might make sense, but we haven't quite figured out how it would all work because we've been able to poke some holes in the idea pretty quickly.
It's an interesting idea. That's all I would add. Yeah, I think you summed it up. There are some holes in that idea with some of the things that did survive and some of the things that got hit really hard.
Ian, I'd like to follow up on my uranium question.
Okay.
Uranium loves phosphate, so it goes to phosphate. So a lot of times dinosaur bones would be radioactive. The allosaur bone on the west side of Dinosaur Ridge just makes my scintillometer scream. So although the phosphatic, you don't need help finding the nodules, the concretions, maybe the phosphatic bone inside would be a reservoir for uranium. And so you could actually discriminate one that has a skull versus one that doesn't based on its radioactivity.
Interesting. Yeah, no, it's a great idea. And James has done some, I don't know if he is on here somewhere. He's done some chemical profiles of these concretions, and I don't know if he looked for uranium or not. There are actually not many volcanic ash beds out there, but we know that just 10 kilometers further east in the basin, the section is just packed with them. So the landscape must have been blanketed in volcanic ashes constantly based on that. But that is really interesting. We'll think about that some more, and yeah, we should chat. Maybe it's a clue. That'd be awesome.
Hey guys, I'd just like to say that I have to jump off for another meeting. You guys continue on with all of your questions. Thank you so much once again, and I'll be talking to you soon. So thank you very, very much.
Yeah, great. Thanks again for having us.
Yep.
Thank you.
And you guys carry on for as long as you want to or can. All right, see ya.
See ya. And maybe just to quickly follow up to Ron or Ronald's comment, in post-COVID times, maybe you can come over. I don't know if you have a different scintillometer than what we have. Again, another question for James, but that would be interesting to try. Oh yeah, here we go. So he's under Dolph Silocker, so he answered everyone there. Dolph is one of our collective heroes, so.
See a question about discoveries of concretions have sent us back to other locations to look for concretion concealed fossils, and that's a great question. You know, as James always says, Mother Nature tends to repeat herself. So it'd be very unusual if this was a unique thing to have these phosphatic concretions. I think it's unusual, but I have no doubt that we will find another deposit like this somewhere in the world. And I have had a few folks email me about this who think they might have some fossils in Morocco or elsewhere that might be in some concretions, and maybe even in some phosphatic concretions. I've looked in my own field areas up in North Dakota and Montana, and I can say that there are no concretions up there with fossils in them, at least that I can see yet. And same with that south of Strasbourg, the picture of the KT boundary. So we think this might have to be to do with something of being maybe, you know, mountain proximal, closer to the mountains. Who knows? We're still really just starting to wrap our heads around this. But I am looking forward to the day when I get more pictures of great mammal fossils in these concretions from other parts like the world, like Bolivia or elsewhere, that have this great interval of time preserved.
Okay, Ian or Tyler, did you see that last question that just came in? What are the distinguishing features about a phosphatic versus carbonate concretion?
I could speak a little bit to that, but I would rather have James, since he's on. This is really his work. He's been really digging into that. Yeah, and he just
They're both ugly.
Could have said it better myself.
Well, yeah.
Yeah, I saw a question. We have published some papers. I know there is a bit of a publication trail. We've published. I think there was a question early on. We had two or three publications so far, and hopefully 2021 we'll have several more. Since we are all working from home and not able to get out in the field as much as we would have liked, we had the opportunity to actually get a few manuscripts written. So I guess that was the upshot of all of this.
And I will mention we actually had a new video come out last week from a group called Seeker, and they do like 10+ minute videos that are really highly produced, and it's sort of about pushing the frontiers, the technological frontiers of paleontology. And so you'll see some beautiful scans in there and some of the stuff at work. I'll send you I'll put a link in the chat here in a second. So ours is 9 minutes long and it's on YouTube. And one of the things that's really cool is it highlights our partnership with the USGS and the USGS drone team, who travels the world documenting these really incredible geological formations for different research teams and all kinds of things like that. They joined us and helped us really image the outcrops down to literally centimeter scale. It's really, really cool. And so you'll see their drone teams in action and the kinds of data they've been able to produce. So I'll throw that in the chat here in a second.
Do you see an iridium spike across the boundary?
We see an iridium spike, not at this location, just because, you know, the depth, the environment was just too fast flowing. You know, usually we get the iridium spike in, you know, the places that are, you know, the slow moving swamp-like depositions. So we get those up in North Dakota. We have it here in the Denver Basin. We certainly have it at the image that Ian showed with all the volcanic ash beds. That's the perfect place to see it, and we do see it there as well. With our section here at Corral Bluffs, we used pollen and the last occurrence of a dinosaur to pinpoint our boundary within about 5 meters. So not that precise versus other places like where we work in North Dakota, Montana, and West Bijou, where we're able to, you know, go and literally put your finger on the boundary clay. But you need a different facies to preserve that.
Any tektites?
Again, not from this interval. Yeah, it's just too fast moving. You know, the tektites land and get, you know, into these river systems and just sort of get churned up versus being deposited in, you know, further in the mountain distal areas where they go into the, you know, the swamps, if you will. And again, we see them there, and we see them in North Dakota. We see them in Wyoming. We see them elsewhere. Just facies is not right at Corral Bluffs.
So Ian and Tyler, you have been amazing and so generous with your time and this presentation today. And we certainly don't want to take advantage of that. I'm seeing one last question here in our chat that I was going to ask you guys, and maybe close out with that, if that works for you. And Dolph, thank you as well for your time. So it's from Jeff May. Do you find the concretions dispersed throughout or concentrated along bedding? And is there any relationship to specific facies or depositional environments?
Yeah, my goodness, Jeff, great question. And it's definitely one that we've been asking ourselves. And yes, there does seem to be some pattern, though we do find concretions in all facies. But it's a question of, how do the concretions look in those different facies, and how they're behaving in the different bedding regimes, if you will. We find entire layers of concretion. So it's basically, it might be a biotically precipitated phosphate, or maybe it's microbial mats or something, but these things seem to be bedded in pond deposits that stretch many hundreds of meters laterally. And then typically they're sort of popping out of muddy or sandy mud facies, though we do get them in full sand as well. One of the things that's interesting is that James has been really thinking about is, could there be a groundwater signal? And so we see some spots where maybe groundwater is moving through. And there's actually a lot of tufaceous textures out there, but those are in carbonate. They're carbonate tufaceous textures. Usually we find them in cavities and big petrified logs and that kind of thing. So anyway, the story's sort of coming together slowly. Lots of different lines of evidence. We don't have a clear answer yet, because it doesn't just, there hasn't been one thing that just has really poked out at us as like, this is why these phosphatic concretions are here. I hope that helps a little bit. A bit of